Hey everybody, we're gonna finish up lesson 23 here with day 3 of lesson 23 of proving the Pythagorean theorem. Again, this is one of the more challenging lessons, and I hope that you get something out of it. You're able to kind of understand why a squared plus b squared equals c squared for right triangles. And today what we're gonna look at that thing, but we're gonna actually reverse it. We're gonna say if a squared plus b squared equals c squared, then it is a right triangle, as opposed to if you have a right triangle, then a squared plus b squared equals c squared. So we're going to look at that a little bit today. And one of the things you're going to have to be able to do is, just a refresher, is to solve basic equations for one variable. And we do that a lot. But I wanted to also just point out that that's going to come back, and we're going to, for you to get one variable by itself. Do inverse operations, add whatever to both sides, subtract so that you are getting something by itself. And that's what we're going to use a little bit today as well. So if you go on to in your notes book, it's on page 208. We're going to work through starting at number 11 here on page 208. So it says sketch a right triangle with legs F, G, and H is the hypotenuse. So do that. Here's my right triangle. Remember, a right triangle has to have a right angle. I got that little thing on the top. Whoops. We got F, we've got G, and we've got H. Again, the hypotenuse, that H word that kind of looks like hippopotamus, that's always the biggest side, the one that's opposite of the right angle. So that's where our H is. It says write an equation relating F, G, and H. Okay. We know that if it's a right triangle, F squared plus G squared has to equal H squared. So whatever number those are, that has to work for it. Now it says, now use what you know about squares and square roots to write an expression for the length of the hypotenuse h. We did this in the last lesson a little bit for a different variable. We're just trying to get the h by itself, okay? And to get h by itself, since it's squared right now, we don't want that. And remember, the opposite of squaring something is square rooting it. So we'll square root that, and we'll square root this side. That'll give us h all by itself, equaling the square root of f squared plus g squared. Okay, so we have a formula then, and if you want to turn it around and write it so that h equals the square root of f squared plus g squared, it just might look a little better that way. Now we have a formula that we can always use if we want to find the hypotenuse. You just square the two other sides, add them up, and then take the square root of whatever you get there. So it says, then choose values for f and g and find the approximate value for h. So let's just say f was, so now we're going to do this part. Let's just say f was, I don't know, 5 and g was 6. If we plug it in, so h would be the square root of 5 squared plus 6 squared. 5 squared is 25, 6 squared is 36. And that totals to, I'll bring it up here, 61. So h would be the square root of 61, which is about, I'm going to say approximately equal to, I checked it already, 7.8. So if the sides for f and g were 5 and 6, you could get h by solving it using that formula. You get about 7.8. All right, let's go to number 12. Number 12, you know a right triangle with legs 3 and 4 units has a hypotenuse of 5. So let's just say we know we have a right triangle. We got 3 and 4 are the smaller legs, and then the hypotenuse is 5. So it's telling us that's true. Now it says use algebra to show that any right triangle with sides 3n, 4n, and 5n work together to make this right triangle, this Pythagorean theorem. So we want to essentially show that 3n squared plus 4n squared equals 5n squared. That's what we're trying to show. Okay. So if I were to take, we're going to have to think back to, this is earlier in the year we did squares, exponents. If it's on the outside of the parentheses, it's got to go to both of the things. So that would become 3 squared and n squared, which would actually be 9n squared. This one we'll do the same thing. So you get 4 squared n squared. 4 squared is 16. And that actually ends up equaling 9n squared and 16n squared. You can combine those. They're like terms. You get 25n squared. Now let's see this one. And square those both. You get 5 squared n squared. And 5 squared is 25. So guess what? We get 25n squared as well. They are equal. Yay! It works. So what we were trying to show is that you can use the Pythagorean theorem for other things. As long as we know that what the side lengths are, you can check it out that way and it'll work. So number 13. A right triangle with side lengths 5 and 12 has a hypotenuse of 13. Okay? 5, 12, we're going to say the hypotenuse is always 13. That's actually true. It says use arguments based on similar triangles to show that triangles with side length 5n, 12n, and 13n is also a right triangle. So one way you can do it is what we just did above. Okay. The other way you can look at it is you could say, since we know similar triangles are proportional, you can multiply them by the same number or scale factor. We can say the sides would all be proportional. And the reason is, I'm not going to put a period there. I'm going to say, because they all are multiplied by the same thing, which would be n. Okay? That's one way you can explain it. If they're similar triangles, they are proportional. The other way is you could set it up the exact same way we did up here. Try to do 5 squared, or sorry, 5n we're using, 5n squared, 12n squared, and show that it equals 13n squared. And I promise if you do the exact same work as above, it will end up being equal. Okay? Let's go on to the next page. Number 14, put it together. It says prove the reverse, or the converse is another name for it, the reverse of the Pythagorean theorem. So the reverse would be if a triangle has sides that make a squared plus b squared equals c squared, then it's a right triangle. So let's just break this down. Where it says part A, start with the triangle ABC. So we've got that triangle right up here, where it is given that x squared is equal to y squared, w squared plus y squared, but the angles are not known. Follow the logic below to prove that angle C, which is that biggest angle, must be a right angle, and the triangle ABC must be a right triangle. Okay, so let's follow along. It says, sketch a different triangle, DEF, with a right angle at F, and where W is the same as FE, so they're the same up above. Excuse me. So, sorry. So we've got a triangle. We've got triangle D, E, F, and it says F has to be a right triangle, so we're a right angle. So we know this one's a right triangle. And we also know that W is the same as FE, so this is the same as W. This is the same as Y, those side lengths. So it says, how can you find the side lengths, or the length of the hypotenuse for DE? Well, since it's a right triangle, we know that W squared plus Y squared, so that's given in this triangle that I just drew, has to be equal to whatever DE squared, or ED squared. So that side squared. Okay, but we also know that x squared is equal to, sorry, we'll say that right here. We also know that w squared plus y squared equals x squared because of, it says it right there. And if we know that's the same, and if you look at the left side, it's the same in both, that means that DE actually has to be the same as x. So this one would also be x. So we know they have the same side lengths then. So let's go to number 3 here. It says explain how you know that ABC, triangle ABC and DEF are similar. So it says corresponding sides are congruent. When all the corresponding sides are congruent, the triangles are similar. Which means, so that's my answer. The triangles would be actually congruent. So the side lengths are all the same. So the triangles would be the same. Congruent, meaning they're also similar. I mean, congruent is actually more specific than similar, but if we know they're congruent, then, I mean, they're definitely similar. That means they have the same angles, they're the same shape. So explain how you know that angle C is a right angle. Well, if they're similar or congruent, smaller, then angles are all equal. And I should say corresponding angles are all equal. All right, last part. And I'm going to leave this up to you. It says, summarize the reasoning above to prove that if a triangle has such sides as a squared plus b squared equals c squared, then it's a right triangle. You can say it a different way, a couple different ways, but it's kind of summarizing everything we've done in this whole lesson. You can draw triangles. You can compare them algebraically. You can compare them geometrically. You can look at any of the examples from the lesson the day before. But we drew a right triangle here. We had the same two side lengths as the triangle and showed that the length of the hypotenuse had to also be the same. So that shows that a squared plus b squared has to be equal to c squared. So you can summarize that however you'd like, but it's a summary of what we've been talking about today and last time in this lesson 23 about the Pythagorean theorem. All right, that's all I've got for today, proving the Pythagorean theorem and its reverse or its converse. See you next time.